Good morning. No snow today in New York City. It's spring weather outside, kind of our first day of warm weather. So I'll probably take the motorcycle out as soon as I finish this talk. So let's see what happens. We're going to continue now with part 2 of poorly named black body radiation, because it consists of more than that. Basically, we're going to look at quantizing continuous spectra, this particular example anyway. And it's to do with radiation. As soon as you take a body, any type of body at all, and raise its temperature above absolute zero, negative 273 degrees or 0 Kelvin, you don't say degrees Kelvin. As soon as you go above zero, the atoms in the body start oscillating, right? And the result of those oscillations is the emission of radiation. We will call that thermal radiation. Now, at first, the radiation is not visible to humans. As the wavelength decreases, long wavelength, or long wavelength, long frequency is invisible to humans below the visible spectrum, all right? And then eventually, if you look at a piece of iron, as it heats up, it starts getting red. So you start seeing the infrared, not seeing it, but then once it goes past infrared, you start seeing that glow, red. Now, an object will go through a series of different colors as it heats up, eventually going into the ultraviolet. And then we can't see it again. We're tuned into the visible spectrum. Doesn't mean the radiation is not there before we can see it. A snake could see it before we could see it. It doesn't mean it's there after its frequency gets so high that we can't see it. No, it's still there. All right? Doesn't get to the gamma region, but gamma rays we can't see either. We'll talk about that. We'll review what spectra are. What do we mean by radiation? This whole topic involves a lot of radiometry, photometry also. Now, we don't really care about that because we're leading into Planck's radiation law, because we're interested in the quantum theory. But it's the quantization of this particular spectrum that we're interested in to continue on with the quantum theory. Now, really, this is an awful lot of physics from the latter half of the 19th century and into the 20th century. So the topic is vast, right? So I have to kind of prune it. But it's very difficult for students to learn because they're just thrown at Planck's radiation law. And then one book will throw it at them in terms of energy density, another will throw the law in terms of frequency, and another one in terms of wavelength. I'm trying to gather it all together. Sorry for the delay, I've been busy with other things. So that's what we're doing. So we'll begin with the following. Okay, so I will quickly mention Kirchhoff's rule, Kirchhoff's theorem, 1859. Kirchhoff, and that he defined the black body in the first place, and he came up with the equilibrium theorem. Then we'll go into, Wien's approximation. Wien's approximation is what Planck's law could reduce to under certain conditions. We're not doing any derivations today. They're coming up later. What I'm doing is gathering it all together for you. From Wien's approximation, you can get Wien's displacement law by taking its derivative. I told you this already. And you get where the peak of this radiation curve is and how it varies with temperature. Right? In other words, lambda max at a particular temperature. So after Wien's approximation, we'll go to the Rayleigh-Jeans law. Rayleigh-Jeans law is not wrong, but it heralds a catastrophe due to Ehrenfest's naming it this. Then that is that the energy becomes infinite at shorter and shorter frequencies, right? And that doesn't happen. Now, Rayleigh and Jeans did not get that wrong. What they did was they employed what was known of classical mechanics and showed, not that the law is wrong, but showed that there was a flaw in classical mechanics. This was cured eventually. Now, from that particular law, we can get Stefan and Boltzmann's law. Stefan Boltzmann's law gives the energy or the power of the entire spectrum. So that means you have to integrate something. Well, in the case of Planck's radiation law, you integrate the whole thing and you get the famous Stefan Boltzmann's constant and the power radiated from any body known its shape. Power. And that's coming up too. But we'll begin with reviewing some basics. So what will I do first? Yeah, I'll review some parameters. Now, a lot of this, the problems for students is to do with notation. One is the following. In American textbooks, you see frequency, which is the number of cycles per second. I will avoid the use hertz, but 1 cycle per second is the same as 1 hertz. It's usually denoted in physics books as nu. Okay? Now, frequency is 1 over the period. And period is the number of seconds per cycle. So if we have a wave, the time taken for these two crests, one tip of a crest to another crest, to go past a point, that's the period. The number of seconds for a full cycle. Now the frequency, if you count the number of crests going past a point, that's the number of cycles per second, that's the cycles per second, that's what the frequency is. Number of cycles per second. So we start getting used to the nu. Speed, wave speed, in this case it's always the speed of light, 3 by 10 to the power of 8 meters per second. So therefore then the frequency we can interchange by the reciprocal of wavelength times a c, and the lambda is c over nu. Okay? Now when we take the omega, which is the angular speed, radians per second, 2 pi over omega is the t. So we can write omega equals 2 pi f. What else? Now what are we talking about here? Well, we're talking about the visible spectrum or the total spectrum of electromagnetic radiation. So we take this to be what we can see. Infrared is down here and ultraviolet is up here. We can tune in our eyes, it's like a radio, we tune the dial, we can see centered on the green where our sun emits most of its radiation, and we could put lambda up here and frequency down here. Now the frequency is the order of 10 to the power of 15 cycles per second in the visible region, and the lambda is about 10 to the power of minus 7 meters in the visible spectrum. So, as we get shorter in wavelength, we get higher in frequency, more crests per second. As we get shorter in longer in wavelength, we get lower in frequency, big gaps between crests. Now, later on, but we haven't done it yet, let's leave out the F for now, okay? So we're getting used to the news. We can go h times nu, Planck's law, comes at the end, but we'll start doing it now. So h over 2 pi is going to be called the reduced Planck's constant. And 2 pi f is omega, so we can write Planck's quantum rule as h nu or h cross omega, okay? A couple of other things I could put in there. Oh yeah. Now, the de Broglie wavelength, P is h over lambda. we can write h over 2 pi times 2 pi over lambda multiplying and dividing. H over 2 pi is the reduced Planck's constant. 2 pi over lambda is called k, the wave number. Okay? Anything else? That's enough for now. These are the basic parameters that crop up all the time. I'll do one more thing. Now suppose we have a function expressed in lambda, d lambda, right? This thing is often crops up, the differential times a function. It's hard to think about what we mean by that, but this refers to the number of wavelengths between lambda and lambda plus delta lambda. But really it has a meaning only when you take an integral over it. We'll do that in a second. If we integrate between all the possible wavelengths, which can go from 0 to infinity in length, we get a scalar number. It turns out a number. So we'll think of this in terms of wavelength. Now this function for us is usually going to be only a function of temperature. Well, not really. It's a function of it. For a particular temperature, we will get some f of t. In other words, temperature is going to be involved in this, and if we have a function, let's say called the radiance. Radiance is going to be the energy emitted per second. That's a power. Now the spectral radiance is the energy emitted per second at a particular frequency or wavelength. We throw in that lambda dependence, and the integral can be taken over to get the actual result. Now, if you want to translate to from the lambda space to the new space, we have to change all the different parameters. But we can write this whole thing in terms of frequency or wavelength. Well, guess what? We could also write it in terms of omega, because omega is 2 pi nu. We could use the omega as well. Guess what? We could write it in terms of energy, because h cross omega. So all of these things, nu, lambda, omega, and e, can be used to specify our particular functions. So that's basically our good start for now. Let's continue. Now there are different ways to approach all of this, and our derivations will come later, but here's where we're going. Now I put the year and dates for these particular things. Everything begins with Kirchhoff. And Kirchhoff did basically two things. He defined or considered what was a black body. Before that, people weren't considering the idea of a black body. A black body is a completely perfect absorber. In other words, if you shine light on it, none comes back to you. But also emitter. Once you go over 0K, it starts emitting radiation in a perfect way. And it can be approximated by a cavity radiator. Right? And then there's an equilibrium rule that we'll talk about in a minute. And we'll come back to Kirchhoff's theorem in detail later on, as we will come back to Planck's radiation law in detail later on. Now, okay. Now, basically, once we've done Kirchhoff's theorem, we can launch into Wien's approximation, which comes in two parts. This one is what Planck's radiation law reduces to. Now, I can't remember if it's long or short wavelength. From this approximation, if we take its derivative, basically we get something that looks like this. We take its derivative, we get lambda 0, where at a particular color, we're going to get a certain lambda. All right? Wien's displacement law, and it's going to vary with temperature, and depending on the situation, we'll have another curve, which is going to be the displacement. That's going to crop up. Now, the Rayleigh-Jeans law is an approximation to Planck's law. Once again, I can't remember if it's higher or lower, but at the opposite. If this was high, this is an approximation at low. This is low, this is an approximation at high. I actually think, hold on, long wavelength, I think, is Rayleigh-Jeans law. And that's heralding the UV catastrophe. Stefan Boltzmann's law is an integral of either of these over a whole situation. And the Stefan Boltzmann's law talks about the total emitted power per area. Now, power, in the spherical case, the area is going to be 4 pi r squared, but that's not always the case. It could be a box, it could be anything else. But we use solid angle in steradians times area in square meters as going to be units for that. Okay, so far so good? All right. Stefan Boltzmann's law is an integral over any one of these things. It's also an integral over Planck's radiation law, and we'll do that job. Now, for these ones here, we can't take an integral properly because the integral will go to infinity. We could really only do it here, but there's a way to show it, and I'll show it later. Planck's radiation law basically holds the key to this entire struggle to lead up to explaining the spectrum of a black body. Now, from Planck's radiation law, we can get all of these, because these are a subset of the great radiation law of Planck in 1900. So 1900 and 1901. So let's see what the history of this is. Okay, so Wien's approximation is for high frequencies, and Rayleigh-Jeans is the approximation for low frequencies, and we write them on the board I think in the next class, because what I want to do for this one is just go over the history. Now, I've done the history before, but I don't want to go too long with this particular class. I'm going to wrap it up after just dashing through the history, and then we'll start writing down equations and doing some calculations. And then the class after that again will be Planck's, Planck. So there's 2 more to come. 3 then, because I'll do some big results, all right? And there's some complicated derivations that I don't mind doing. This is a general chat. It's leading up to all of that. So in terms of the history, Kirchhoff's theorem is 1859, but he lived between 1824 and 1877. Wilhelm Wien lived 1864 to 1828. And the approximation is done in 1896, the actual paper. Now the displacement law follows from that, so that's in the same year because it's just a derivative. Rayleigh genes, James Strutt, Baron Rayleigh, and James Jeans, that law, well let's see, John Tyndall is in here because John Tyndall did the experimental work upon which Wien based his model, okay? John Tyndall lived between 1820 and 1906. Joseph Stefan. Joseph Stefan lived between 1835 and 1893, and Ludwig Boltzmann. (1804) to when he committed suicide in 1906, and the law itself was derived in 1884. Okay? The Rayleigh genes law, I don't have a year for. Then we have Max Planck. He lived between 1858 and 1946, and he has two publications. A long German paper, which is, I can't read the name, something, VDPSG, it's a long publication, but the first paper was in a German journal in 1900, and the second one was in Annalen der Physics, volume 4, page 553 in 1901, that's his second paper, Max Planck, and thereafter we get the quantum theory. It was actually Einstein who came up with the idea of photons of light. Even though there are photons appearing in here, he talks about quantizing the energy of an oscillator. Okay? Now that's where we're heading. That's lesson number 2. Let's hold it there because that's a lot of detail to swallow, and I'll come back doing each little particular part individually in the next one.